Now let's see what is the image formed by the mirrors or lenses when we put an object in front of these optical devices. We define curved mirrors as mirrors which looks like a portion of the sphere. In general, we can have two types of the curved mirrors. Either we have a concave mirror which looks like this shape, and we have basically, this is the back of the mirror, and we put the object in front of that, for example, if you like. Or we can have a convex mirror which looks opposite to that, and in this case we have basically the object in front of the curvature like this. We have two other different names as well, for these two as well. For example, the concave mirror is also known as converging mirror, and the convex mirror is also known as diverging mirror. We will see why we call them like this a little bit later. Similarly, we can also define lenses in two different types. We have concave lenses or convex lenses. So similar to what we said here, a diverging or concave lens looks like this. So it looks concave on both sides. And a converging or convex lens looks like this. It looks convex in both directions. So sometimes to have a little bit easier pictures to draw with, we show the convex or converging lenses by these simple arrows as well, and the diverging or concave lenses by opposite basically arrows like this. There are different notations we have for lenses. But let's see how we can find the position or the conditions of the image produced by each of these optical devices. First of all, we need to learn how we can look at the ray diagrams. In ray diagrams, we're going to start from tip of the object, shine light toward the lens or the mirror, and then predict what would be the resultant image by looking at the ray diagram. There are three different types of the rays we use to find what is the position and conditions of the image. One of the rays is going through the center and continue straight. Let me explain them by showing you one of the curved mirrors. Imagine, for example, we talk about the concave mirror like this. So remember that the concave mirror is portion of the sphere. So it means that we can basically consider the full sphere, if you like, here, and then we call the center of this sphere or center of this circle you can see in the picture to be point C. Then we define point F to be half of the distance between the point C to the actual mirror. This is point F, which is also known as focal point. The distance between the point F and the mirror is basically what we define as focal length. So the first type of the rays we have would be the ray which is going to pass through the center of this sphere that the mirror is basically made of. If I want to show it here, let me use the red color for that. This ray is going to pass through the center, hit the mirror, and is going to reflect back on itself. That's a first type. The second type is the ray which is parallel to the axis of the curvature and comes out through the focal point. The line shown here with the green color is basically what we have as the axis of the curvature. And then if I want to show you the ray described in the second one, so the ray is going to move straight parallel to this axis, as you can see here, and after reflection is going to pass through the focal point F. So that would be this ray here. That's the second type. And finally, the last type would be a ray which is going through the focal point and then comes out parallel to the axis of the curvature. That's a kind of reverse of the pink ray showed here. Let me use the different color for that. Imagine we have a ray which is going to pass through the focal point. Let's, for example, consider this one. So after reflection is going to reflect back parallel to the axis of the curvature. This is the third type. So we can use any two of these possible rays to find where is the location of the image produced by each of these mirrors or lenses. But let me explain to you a little bit why we call, for example, the concave mirror to be converging and we call the convex mirror to be diverging. Let me look at this concave mirror once more. If I shine light parallel to each other into this concave mirror like this, imagine, for example, we have an object in a really far away distance, and the light from that object is going to hit the mirror in parallel directions. As we discussed earlier, if I have a ray which is parallel to the axis of the curvature, that's a type 2, in that case, after reflection, it's going to pass through the focal point, which is basically point F here. It means that all these parallel rays are going to reflect back from the mirror and going to pass through the focal point. So if I want to show them here, they're going to be something like that. So as you can see, all these lights are going to converge into the point F, focal point. So that's the actual property of this type of the mirror, which is basically concave or converging mirrors. Now let's look at the convex mirror. If I have a convex mirror, this is the back of the mirror, convex. And as you can see, the curvature would be toward right. That's why the focal point we have would be basically on the right hand side here. Now still, I'm going to put the object at really far away distance, and I'm going to shine lights coming from the object in parallel direction toward the mirror. We said that if I have the lights parallel to the axis of the curvature, they have to pass through the focal point. However, notice that since the focal point would be on the right hand side, and we know that there is nothing basically behind the mirror, we have to look at this ray, which looks like that is coming from the focal point basically. Similarly, for the second ray, we have to look at this line, which is coming from the focal point again, or similarly for the other one. So if I want to show you the hue, so this is actually how we determine what is the direction of the reflected wave. As you can see, in this case, if I shine parallel lights toward the convex mirror, all these lights are going to diverge respect to the mirror after reflection. That's why this mirror is known as diverging mirror. Okay, now let's look at the type of the image we can produce by each of these devices. So we can talk about the image produced by each of these optical devices. If I look at the intersection of two rays out of the three options I mentioned previously, if you put the object in front of the mirror or the lenses. But the important point is that sometimes we may need to trace backward and then try to look at the intersection of the rays, because they're going to be diverging rays, and in order to look at the intersection of these two, we have to trace backward. But when you trace backward, basically the point of intersection doesn't exist in reality. So that's why we call this kind of the images to be virtual images. In general, we can have different properties for the image formed by putting an object in front of the mirror or a lens. Either we have a real or virtual image. As I mentioned, if you make the image by intersecting of the tracing back of the actual rays, in that case, since basically the image doesn't exist in reality, we call it virtual image. But if the image is basically formed by intersection of the actual light rays, in that case we have a real image. This real image could be also shown on the screen. That's another way you can talk about the real image, because for example, if you put a piece of paper on that location, you can see the actual shape of the image on the paper. The other property we can talk about the images would be being upright or inverted. Sometimes, for example, if I put a arrow which is pointing upward as the object here, the image produced by that is also looking upward. Sometimes the image looks downward. If it's looking upward still, we call it upright image. But if it's looking downward, in that case, we call it inverted image. And finally, the image could be either larger or smaller compared to the actual size of the object. By tracing the light rays after reflection from mirrors or after refraction from the lenses, we should be able to answer questions like what type of the image we have, is the image bigger or smaller than the actual object, or if the image is inverted or upright. Let's try to practice a little bit and see how we can, for example, guess what type of the image we have for different scenarios. In this picture, I have a concave mirror, so it means that basically this is the back of the mirror. And point C here would be basically the center of the sphere that the mirror is made of. And as I mentioned earlier, point F, which is the focal point, would be half of the distance between the center and the mirror. In this case, we put the object, which is an upright arrow, at this position. And then I want to look at the image produced by this concave mirror for this object. Pay attention to the position of the object. In this case, I put the object out of point C. It means that this object would be outside the focal point and outside of the center of the curvature, which is point C. If I put the object here, let's see how we can predict what type of the image we're going to produce. I'm going to consider two different rays. One of them would be a ray which is going to move parallel to the axis of the curvature, and based on what we discussed, this type of the ray, after reflection, is going to pass through the focal point, as shown with the dashed line. That's a first type of the ray I consider here. The other one would be, for example, the one which is going to pass through the focal point first, and after reflection, that should be parallel to the axis of the curvature. Notice that even you can also consider the third type of the ray, which was the ray which is going to pass through the center, and it's going to reflect back on itself. But let's look at the intersection of these two rays I showed here. If I look at the intersection of them, it's clear that these two rays are going to meet each other at this point. It means that the image we have here is going to be formed like this. Now from the picture, first of all, the image happens to be between F and C. Second of all, is going to be inverted with respect to the original object. And as you can see from the picture, it would be smaller. Let's talk about being real or virtual. Because this image is formed by hitting the actual two rays. In that case, we have a real image. That's why we have a real image, which is inverted and is smaller. If I put the object in different positions, for example, between C and F, or inside the focal lens, or basically between the mirror and the focal point F, in that case, we're going to have different results. However, as long as I put the object on the left-hand side of the center, we always get an image which is real, inverted, and smaller than the actual value. I don't recommend to memorize these properties we have for the images, because you can immediately put the object in the appropriate location and try to look at the ray diagram to predict what are the properties of the image produced by that one. Let's look at some more examples. For example, here we have another concave mirror. Still we have this lens as a back of the mirror. And now I want to put the object inside the focal point. It means that, as you can see in the picture, object will be between the point F and the mirror. And I want to guess what type of the image we have here. Let's do it together. First, I'm going to look at the, for example, one ray which is parallel to the axis of the curvature. We said that this type of the ray, after reflection, is going to pass through the focal point. So that gives me this line. Let me have a better one to pass exactly. Okay. It's really important to have an accurate picture. Otherwise, you might be misled by the position of the image. That's the first one. For example, let's consider the other ray to pass through the center. We said that if I have a ray which passes through the center and pass through the tip of the object like this, it's going to reflect back over itself. So it's going to reflect back in the same direction. Now, as you can see, after reflection, these two rays are going to diverge. It means that we cannot look at the intersection of these two lights on the left-hand side of the mirror. That's why we have to trace back these rays. And we see that these two rays are going to meet each other at this location behind the mirror. The image we have here would be something like this. So as you can see, first of all, since I couldn't look at the intersection of the actual light rays to form the image, and we have to basically look at the tracing back of the lights, in that case, we have formed a virtual image. Furthermore, it's larger compared to the size of the actual object, as you can see here. And finally, it's going to be upright because we didn't change the direction of that. Now let's try the same thing, this time with a convex mirror. If I have a convex mirror, it means that now the back of the mirror would be here. But notice that because I have the convex mirror, now the focal point and the center of the curvature would be beyond the mirror. So that's why we showed them on the right hand side here. I put the object at this location and I want to see what is the form of the image we form here. I consider two different types of the rays. First of them would be the one which is going to be parallel to the axis, for example. This one should pass through the focal point. However, since the focal point would be on the right hand side and basically there's nothing on the behind the mirror, in that case we assume that this light is going to pass through the focal point coming from that one. As we expect for the convex mirror, the lights are going to diverge after hitting the mirror. The other ray I consider here, for example, would be the one which is going to pass through the focal point. So if I consider the other one, this one is going to pass through the focal point like this. So we expect this one to reflect parallel to the axis. So it means that at the moment it hits the mirror, it's going to reflect back parallel to the axis. This is two different rays we consider here, but we can see that the blue ray here and the pink ray, they are going to diverge from respect to each other. That's why we cannot look at the intersection of them on the left hand side of the mirror. As a result, we have to trace back these rays and look at the intersection of them behind the mirror on the right hand side. If I look at the intersection of them behind the mirror, they're going to intersect each other at this point, and this is the shape of the object form here. Sorry, the image form here. Notice that this image, first of all, happens to be in the focal lens, is going to be a little bit smaller in size, and is going to be also upright. Furthermore, since it's made behind the mirror or is made by not actual intersection of the rays, that's why we have a virtual image. We can repeat the same argument even for the lenses as well, but for lenses we have to be more careful because we don't have reflection here. Instead of that, we have refractions because lenses are transparent and light is going to pass through them. However, because we're going to change medium for the light, they're going to have some refraction. But the idea would be the same, and we can use the same type of the rays to describe the image produced by different lenses. For example, let's look at a convex lens and see what we get here. I put the object at this position out of the focal point, if you like, and then I want to see what is the shape of the image. So first of all, I'm going to look at the ray which is going to be parallel to the axis of the curvature. This ray should pass through the focal point. However, since we have a transparent lens, it's going to pass through the focal point on the right hand side of the lens. So that would be this one. Similarly, if I look at the other one, for example, the one which is going to directly pass through the center of the lens, in that case, is going to pass through the center of the lens without any basically deformation. Now these two lights are going to hit each other at this position, and notice that their actual lights meet each other. It means that the image I form here would be a real image. If I put for example, a piece of paper in this position, I can see the actual image on the paper because the actual lights are going to meet each other at this point. So we have a real image. Furthermore, is inverted, is upside down. That's why we have inverted image. And finally, it's larger than the initial object. Now let's look at another example. In this example, I put the object in a different location. Now we are inside the focal lens, or basically between the lens and the focal point. This is the object, if you like. So again, I consider two different rays. The first one I consider here would be the one parallel to the axis, and that should pass through the focal point on the other side. So that would be this ray. The other ray would be the one which is going to pass through the center of the lens, and that's going to go directly without any refraction. Now, as you can see on the right hand side, these two rays are diverging, so we cannot look at the intersection of the actual light rays. However, if I trace them back, they're going to meet each other on the same side as the object at this location. Because this image is formed by intersection of the tracing back of the light rays, not actual light rays, that's why we have a virtual image. Furthermore, from the picture, this virtual image has larger size and is upright. These are actually the properties we get here. So in this case, if I put a object in the focal length of a convex lens, in that case, we produce a virtual image which is basically larger in size and is also upright. We can also look at the concave lenses. Let's look at two examples of those cases as well. For example, here we have a concave lens with the focal points shown here, F and F. And let's put the object at this location out of the focal point. But remember that this concave lens is also known as diverging lens. It means that after refraction, the light is going to diverge away from the center. It means that, for example, if I look at this ray, which is parallel to the axis of the curvature, after refraction is going to basically refract away. But as usual, we expect this refraction happens to such that the ray is going to pass through the focal point. That's why this time is going to pass through the focal point on the same side as the object. This is different from what we had for the convex lenses. For convex lenses, if I have a light parallel to the axis, it was going to pass through the focal point on the other side of the lens. However, for the concave lenses, if I have a light parallel to the axis of the curvature, the refracted ray is going to pass through the focal point on the same side as the object. That's why basically we are going to look at this kind of the ray, which looks like that is coming from the focal point on the same side as the object. And then the other light ray I consider here is the one which is going to directly pass through the center. If you have a light ray which passes through the center of the lens, in both cases, is go directly pass through the lens without any refraction. Okay, so now you have to look at the two rays we have on the right hand side. Clearly they are diverging, and as a result we cannot look at the intersection of the actual light rays. We have to trace them back and look at the intersection of them on the left hand side of the lens. This is the image formed here, which happens to be in the focal point, smaller than the actual object and upright. And since it's made by the tracing back of the actual light rays, it's a virtual one. Okay. And the last example I want to show you would be here. Let's do it together here. Now we have an object in the focal lens of a concave lens. The first ray I consider here would be the one which is going to move parallel to the axis. And as I mentioned, since we have a diverging lens here, we look at the refraction, which looks like it's coming from the focal point on the same side of the object. That's the first ray. The other one I consider would be the one which is going directly passing through the center. So again, if I look at the right hand side, these two rays are diverging, so we cannot look at the actual intersection of them. We have to trace them back. So it's clear that if I trace them back, we end up at this location, and this is the image we produce here. The image would be still in the focal point lens, is upright and virtual. So it means that for the concave lens like this, no matter where I put the object, we always get the image to be upright, virtual, and within the focal point. And it's also always smaller than the actual object. So far we learned how we can look at the ray diagram and predict the conditions and the position of the image formed by each of the mirrors and lenses. But let's see how we can find this information from the equations. We have two equations which are really useful. One of them is known as the mirror lens equation. The other one is known as magnification equation. Let's look at each of them one by one. Mirror lens equation would be the top equation, which is 1 over O plus 1 over I equal to 1 over F. Here O would be the distance between the object and the mirror or the lens, and I would be the distance between the image formed by the mirror or the lens to the mirror or the lens. And F here is the focal point, or distance between the focal point and the mirror or the lens. Furthermore, we have magnification equation, which tells you how much the image is basically changed in size compared to the original object. Magnification is defined as minus I over O, when I and O has the same definition as what we had for the mirror lens equations. And we can also write it down as HI over HO, when HI would be height of the image and HO would be height of the object. So basically, if I know what is the ratio of the height of the image and the object, that tells me how much the image would be bigger or smaller compared to the actual object. So using these two equations, we can answer questions like this. Where is the image location? Is the image real or virtual? Or basically, is the image upright or inverted? Because, for example, here in this equation, if we have a upright image, h would be a positive number. However, if we get a negative value for the h, it means that we have an image which is inverted. But in order to use this equation and get the right result, you have to be super careful when you want to plug the information there, and you need to know that how to interpret the result coming from these equations. That's why we have certain rules that we have to pay attention to them whenever we use these two equations. Let me go over all these rules once more and try to remember what is the basically sign of each of these parameters when we want to insert them into the equations. First of all, O, which is the distance between the object and the mirror or the lens, is always positive in the equation we have above. That's easy to remember. And similarly, we always consider HO to be also positive. That's a height of the object. Now for the mirror, for the eye, which is the distance between the image and the mirror or the lens, we have a certain criteria, which is different for the mirrors and lenses. Based on what I wrote here, I would be positive for mirrors if the image is formed on the same side as the object. Basically, it means that we're talking about the real image for mirrors. Similarly, I would be positive for lenses if the image is made on the other side of the lens compared to the object. Again, we know that if I have a lens and we are going to look at the real image, that is going to be formed on the other side of the lens. That's why I would be positive if we have a real image. So to summarize these two sentences, as long as you have a real image, in both cases, both mirrors and the lenses, we have I to be positive. So you can immediately conclude that if I have a virtual image, I would be a negative number. That's the first thing. The other thing I want to mention is that we also have some certain convention for the F, which is the focal length. If I have a concave mirror or a convex lens, in that case we consider F to be positive. Just to remind you, a concave mirror would be this one, and the convex lens would be this one. However, if I have a convex mirror or a concave lens, in that case we consider F to be a negative number. Just to remind you, convex mirror looks like this, and concave lens looks like this. So basically, if I have a diverging object like the convex mirror or the concave lens, in that case F would be negative. So basically, if I have a converging object like concave mirror or the convex lens, in that case F would be positive. However, if I have a diverging device like convex mirror or concave lens, in that case F would be a negative number. So to summarize everything together, we would say that if I is positive, first of all, it means that, as we mentioned earlier, we have a real image. And from magnification equation, since h is equal to minus I over O equal to HI over HO, if we have a positive I, we have a negative value for the M, which means that HI over HO should be also negative. So if HI over HO is always negative and HO is always a positive number, it means that height for the image should be a negative number, which means that the image would be also inverted. That's why if I is positive, then we have a real image, which is also inverted at the same time. Similarly, if I have a negative I, as we discussed earlier, we have a virtual image. But from the same equation here for magnification, if I set I to be negative, that makes the M to be positive, which means that the ratio of the heights is positive. As a result, we have a positive value for the height of the image. So it means that the image would be upright.